All right, so I think we can get started. We have about a minute left, but people can just trickle in. So thanks everyone for coming. My name is Igor Grasnov. I'm from Nice Systems, and I'm going to be talking about business rules on Hadoop today. So just to show of hands, how many people here know what business rules are? Awesome, that's great. How many people know what Hadoop is? I hope everyone. Awesome. So we're Nice Systems. So what my team does is we analyze call center data. We do a thing called next call prevention, which is looking at trends about what people call, who they call, and making sure that their problems get resolved on time and with the first and at worst second call, so they don't call back. And this is part of a more general scheme called call volume reduction. So we have a big data platform. That's me. I work on that. And on top of it, we have applications all geared around this call center data analytics. So what are business rules? A quick overview, even though it looks like everyone here knows. So business rules are meant for decision logic. We want to make decisions based on data. And these decisions can be very simple decisions, such as if the person is over 21, then they can drink, otherwise they can't. Or they can be something different, like if a customer buys 2 items, then get them 1 item free. Business rules can be used to automate processes. They're very useful for this. They can enforce policies, and they can perform ETL automated. You just set up the rules. As soon as the new data comes in, then all your policies get enforced, all the ETL happens, everyone's happy. And the main way that business rules get used are through business rule management systems. There's a lot of these around. iLog and Drools are big ones. We use both of them right now at Nice. And these management systems are used to write, manage, deploy, execute, and monitor rules. Pretty much the whole life cycle, beginning with I only have data to I want my data processed in this order at this time, and I want to edit my rules. All that gets managed by these management systems. So how do business rules work? So you have data, and then you write your rules, and then some magic happens, and then you make profit out of that. But how do they really work? This is a simple diagram. So you have data and rules. Usually separately, data is coming in from an external data source. The rules are written internally or by your customers, depending on how you're deploying this. They both get fed into a rules engine, which is the key part here. The engine compiles the rules, runs them against the data set, and then produces your results. On a more technical scale, the way this works is that you need Java beans to hold your data. You create these beans, you feed each record into its own bean, and then you write the rules to describe the logic you want to perform on these records. And usually the rules are pretty simple, and they're based around what beans you have. So you can do something like customer.get total and cart. Something like, usually they're shorthand for the actual Java objects that you have. You stick all the beans into the engine, you stick all the rules into the engine, and then the rules get executed against those objects. But you want to get results. And usually there's 3 ways that we use business rules. We either modify the objects in place, so we update a field based on these rules calculations. We create new objects that we then return and persist. Or we write out whatever we processed into a database, into a file, what have you. So why do you want to use business rules? Because not everyone knows how to program. A lot of this would be done very easily if you knew how to write code. All this logic can be just written in code, and it's very easy. However, a lot of analysts can't write code. But business rules, on the other hand, are very simple to write. A lot of the times, they look a lot like English. They look when the customer has purchased more than 2 items, then add a gift. There's also nice GUIs available, so you don't always have to memorize the syntax. You can simply kind of drag and drop, plug and play, and design these rules without really knowing what the underlying objects are or how it's being executed or what it's doing underneath. Also, a very useful thing is that this is a one-time infrastructure setup. Once you have your rules engine in place, once you know how you want to process it, where you're getting this data, the rules simply just plug into that. The data keeps coming in. If you want to update the rules, you update them, put them into the existing infrastructure, and everything's set up. That'll just be run as long as there's no issues with the rules that you just put in. So why do we want to run business rules on Hadoop specifically? Business rules typically are very memory intensive. This is due to the way that these rules engines are implemented. They create a lot of internal objects that take up a lot of heap space in Java. So once you get into processing millions, tens of millions records against these rules, and especially if the rules get more complicated, your internal structures are going to get huge and simply blow the heap space on one machine. You could also have hard calculations with medium-sized data. By hard calculations, I mean complicated decision logic, such as complicated math operations, pseudo-joins. By pseudo-joins, I mean we're not talking SQL. We have one file, another file, we're joining them. By pseudo-joins, I mean if this field is equal to this field in another object, then process these two objects together. And then we also have easy calculations on huge data sets. We have row-by-row calculations, like I said in the beginning, a simple if age is greater than X, then do Y. And aggregation. Aggregation is typically very simple to do. However, when the data sets get very large, sticking all of the data into memory to process it at once, that becomes a problem. Another reason to run business rules on top of Hadoop is scaling. This is very important for us at NICE. We currently have an application that runs Drools rules against call center data. However, as we get more data in, we need to process previous data along with current data. Scaling this has become an issue. These rules are getting to the point where even multi-threaded, we're still running into the hours for processing this. We want to do this much, much faster. So the next logical step for us was to move on to Hadoop and build this whole infrastructure. Since we're building the infrastructure on top of Hadoop, we'll simply process the business rules also on top of Hadoop. But don't get too excited about Hadoop and business rules yet. There's a lot of limitations, and a lot of these are simply native Hadoop limitations, MapReduce limitations that you can't work around even though you really want to. Calculations that require access to the full data set, such as calculating an average of billions of numbers, you can't really do that in MapReduce by itself, and just because you added a rules engine on top of it doesn't mean you'll be able to do it now. This is a MapReduce limitation. You need a way to break up your, the rules can't have access to the full data set all at once. If there's too much data for one key and you have a reducer and you're outputting 90% of your data into this one key, for example, a big problem for us was there was a key that was null, and therefore all the null objects were simply going to that reducer, and it was blowing heap space, running very slowly. Why is this happening? You need to have diverse keys, otherwise it won't work. But once again, this is a native Hadoop limitation. And also, if you're passing objects between mappers and reducers, you need to serialize your objects. This is, once again, only an issue if you have a reducer, because if you're just doing calculations in the mapper, you can simply pass in the object and do the calculations there. If you have a reducer, the mapper needs to serialize the object in order to pass it to the reducer. And when it does that, it needs to know that this object is serializable and how it's serializable, and the reducer needs to know how to deserialize it. This is a problem for custom objects only, but since with business rules, you're often creating Java beans that are holding all your information already, then this often becomes a problem. It's easy if your objects are small and simple, like I will show you in the example, but when you're getting into more complicated objects, into nested objects, if you have a custom object and then you have a custom object within a custom object. That needs to be serializable, and you can see how this can get very complicated very fast. So I have two examples of actual performance of standalone business rules engines and business rules on top of Hadoop. And my examples consist of agents making sales. You have agents in a store, and they're making sales, and there's some returns, which accounts for negative sales in data. This is fake generated data. I made it up myself because I just needed examples. Different types of calculations. You will see calculations that are row by row, meaning the engine only needs access to one object at a time in order to do a calculation. And then there's the second type of calculation where the engine needs access to one or more objects in order to do its processing. These are the two main distinctions in rules as far as when it comes to processing on top of Hadoop. If the engine only needs access to one object at a time, which is a simple if-then statement, then you can do work in the mapper, because each mapper will just have one object, you perform the calculation, you spit it out. If it needs one or more, such as with aggregation, then you need to pass that into the reducer, and this becomes a totally different type of calculation. The mapper might be doing minimal to no work. It might just be a simple pass-through mapper. And running all these examples, I've compared the performance. There's going to be some pretty graphs and some formulas. I'll explain that when we get there. So our two test scenarios, the first one is how much bonus should an agent get based on the current sale? A simple formula, if the sale is more than 0, which is an actual sale and not a return, then get 1% of the sale as a bonus. Otherwise, you get nothing because it's a return. In this example, all work is done in the mapper. Since this is a row-by-row calculation, we can simply collect these objects in the mapper, stick them into the engine, process them, and then at the end collect all the output of all the mappers, and we have our final result set. The second example, a little more complicated. What is the total number of sales that the agent has made across the whole data set? This is more complicated because the mapper here can't do all the work. You don't know which data is going to what mapper. So in this scenario, the mapper is simply a pass-through mapper. It takes the data that is passed to it, and it outputs it back into the reducer. The reducer then picks it up, aggregates it by the key, in which case the key here is the agent name, and all work is done in the reducer, meaning the engine is sitting in the reducer. It does the calculations based on keys, and then outputs the final result. Any questions so far? No? Great. So here's my agent sales bean. Implements writable. Note that implements writable is what I was talking about earlier. This is the serialization part of passing in between the mapper and the reducer. You need to specify two methods, one for how is this object serialized, and one for how is this object deserialized. We have 4 fields, 2 strings, an int, and a double. Fairly self-explanatory, followed by getters and setters, serializers and deserializers. The object is not big. I wanted to keep this small so I could scale this out into a huge number of records at a time. All the names are generated randomly. It's from all alphabetic characters, a string of length 5 generated randomly. So when you're getting into millions and millions and millions, you will see repeats. This is why the second example works. So a little more detail on these examples. We have a file pipe delimited with all these records. One record is one bean. For the first test, we run 50 million, between 5 and 50 million records at a time in increments of 5 million. For the second example, it's a little more intensive. We run between 1 and 5 million in increments of 1 million. And Hadoop gets a little bit extra data for that one just to see how far we can push the performance on it. Just to give you an example of data size, 1 million records is about 23 megabytes. So you're looking at over a gig for some of these larger examples. Once again, we're not talking huge data sets. We're really talking huge data volumes in terms of number of records, not in terms of sizes. But the size is also not negligible. A little more details. These are the machines that have been running the examples. The standalone machine that is running, just the engine, and I feed the data into it. It's a 3.3 gigahertz with 4 cores, 9 gigabytes of RAM allocated to the JVM. Our cluster consists of 3 data nodes, 2.4 gigahertz with 16 threads, 8 cores available to it, and 2 gigabytes per mapper with a total of 32 gigs available per node. We're never going to be blowing memory on this one. So just to recap, the first scenario, if-then statement, very simple, row by row calculations, all work should be done in the mapper, nothing gets passed on to the reducer. Let's see the results. So the green boxes are the standalone run. The blue diamonds is the Hadoop run. As you can see in the beginning, the standalone is faster. As you can expect, Hadoop has a significant spool-up time. The JVM needs to launch, it needs to write out, close all the processes. This takes a while for Hadoop. So everything up until what it seems like almost 10 million records, about 7 million records, you're looking at standalone running faster. However, the problem with the standalone engine execution is that it scales much worse. As soon as the more records you add, it'll scale linearly, but as well as Hadoop will. However, it will scale twice as slow. As you can see, the coefficient for the X is the number of records in millions at this point, and the coefficient for the standalone is 6.5. So you're looking at 6.5 seconds per extra million records, whereas the Hadoop one is 3.3 seconds per extra million records. Twice as fast, but both scale linearly. A summary of this, neither implementation ran out of RAM. Never had a problem with this. However, I had to clear out the working memory for both of these simply because if I stuck too many objects into it, it would blow up. Once again, this is due to the fact that the engine is creating a lot of internal objects, taking a lot of memory. This was a big problem with the standalone, but an easy solution for this is once you process a million records, 500,000 records, just clear out your whole working memory of the engine, stick the new next 500,000, process it, and just keep going until you finish everything. Both implementations grow linearly. However, the standalone grows twice as fast. Second scenario, recap again. This scenario is a simple summation of all the sales done by the agent throughout the whole data set. In this case, this is where it gets tricky. We have a pass-through mapper that simply takes the record and outputs it. The whole mapper is about 3 lines of code, which is read in the record from the file, create a bean out of it, and stick it into your output. The reducer, however, picks up that record, deserializes it, but since the record key that you're outputting is the agent, the reducer will have every single record for that agent, regardless of your data set. This is how MapReduce works. And we can exploit this in this scenario, and in any aggregation scenario, really, in order to sort of pre-sort the data. It sorts it by the agent and then passes all the data for that agent into its own reducer. And our data set was fairly small. Each agent had at most 5, 6 records at a time. Therefore, each reducer was simply processing a lot of keys. But we had a lot of reducers. So this simply sped everything up because we were able to parallelize it. As you can see the results here, once again, a similar thing happens. The standalone runs much, much faster for smaller data sets. I mean, we're even talking about closer to 4 million data points. However, it scales very poorly. We're looking at 15.5 seconds for an extra million data points. Whereas the Hadoop one takes forever to spin up, over 30 seconds, as you can see here. However, for additional data, it processes it much, much faster, 6 seconds for a million data points. So the interesting part here, you'll see the standalone line breaks off at 4 million data points, so you might be wondering, well, why is this? Where's the 5 million? Did it not fit on the graph? Is it exponential afterwards? No, it simply blew out of memory. The reasoning for this is because in the standalone, when you need to do aggregation, it needs to know all the data. It can't know if it got all the data for a specific agent in the beginning. In the end, it doesn't know where all this data is. Unless you pre-sort it and specifically tell the engine that, yes, the first 5 records are for agent A, second 10 records are for agent B, then it can get smart about it, start clearing its working memory. Otherwise, it needs to keep every single record in its working memory. Therefore, after 4 million records in its working memory with all the objects associated with it that the engine creates about the rules, it simply blows through 9 gigabytes of RAM. It's fairly obvious to see here that if this line was to continue, though, if you say hypothetically you had a machine with 16 gigs available to the JVM, 32 gigs available to the JVM, it doesn't matter. This line will grow much faster than the Hadoop line. But since this is a simple up to 5 million, this is no fun. I want to see how Hadoop actually does with larger data sets. What about 10 millions, 20 million? Well, let's look there. Like I said, the standalone ran out of 9 gigs of RAM at 5 million records. The Hadoop never did. It ran up to 50 million records. And it ran 50 million records in about, sorry, back. So this is about a minute for 5 million. 50 million actually was around 3 minutes. So the scale is very, very good here. Hadoop was running on a lot of reducers, however. We were looking at 24 reducers running at 600 megs of memory allocated, which is the default setting. Aside from the 24, you have to base this on your cores, number of nodes. You can do some fine-tuning yourself. And getting the data there took a long time. This isn't how long it took to process. As you can tell from the graph, oh, sorry, I'm going back and forth. The funny thing is, for the 1 million records, it took about 38 seconds maybe. However, out of those 38 seconds, about 20 to 25 of those weren't even in the reducer in the first place. They were either spooling up the JVMs or passing through the mapper, getting the data out of the mapper into the reducer. So there is that significant lag time for Hadoop that you need to be aware of. And if you want to run this on a small data set, such as 500,000, it just won't make sense. It'll take forever for the data to actually get to the processing stage. MapReduce scaled very well in this scenario, but this is actually because I exploited the way that MapReduce is built. I used MapReduce pretty much to sort my data for me, and then I told the engine, your data is already pre-sorted, just go at it. Was I cheating? Was I not cheating? I don't know. That's up to you. You decide. But perhaps this is why Hadoop is so good for this sort of calculation, is because you can exploit these sort of paradigms that are built into MapReduce and use it to speed up your data, so you don't have to load the whole data set and wait for it to give you an answer. Also, another interesting thing is that everything, even up to 50 million records, can be run on just one reducer running 600 megabytes of memory. How, you might ask? Because, like I explained before, I'm sorting the data and I'm passing it in. The reducer then takes every block of data, runs it, and then clears its working memory and takes the next block of data. Therefore, using MapReduce, I can spawn a very, very small JVM and process a huge amount of data without ever having to worry about RAM. This is one of the most amazing facts that I got out of this experiment. And just to give you an example of how long it takes, 50 million records running on one reducer took 18 minutes. So not even that bad, considering the fact that you only have to use up one reducer slot on your whole cluster to run this. Let's look at some conclusions from my experiments. A lot of memory is required, especially for complicated rules. If you have aggregation rules, If you have complicated logic, you're looking at a lot of memory, or a huge memory requirements. This depends a lot on how you implement your rules, how you write your rules, and how your engine is implemented, what internal structures it generates. You have to read up on the implementation of your own engine. There's a lot of engines out there. This isn't the time for me to cover how all this is being processed. Use Hadoop only for very large data sets, huge data sets even. Don't bother spooling up a cluster for 500,000, 1 million, 2 million, 10 million even, really, except for those aggregation examples that I was showing you. Because you're gonna lose time on the JVM startup as opposed to the standalone engine, which can simply spool up and go right away. The cutoff size for how many records is a lot depends on you. It depends on what kind of rules you're running. It depends on what kind of objects you're analyzing. It depends on how big the objects are. Kind of look at your data set, look at your memory requirements, look at your rules. If these are simple rules, then clearly the cutoff is much higher. And finally, Hadoop scales very well. I'm sure we all know this. This is why we're here. And Hadoop scales very well, especially with these subset calculations, where, as I described earlier, there are calculations that require only access to one object at a time, and calculations that require access to one or more objects at a time. This one or more, if the keys are evenly distributed and the rules aren't very difficult, then this will run very well on Hadoop in the reducer. So you might be wondering to yourself, how am I actually going to implement this? How do I build this? You didn't show me any code. Well, everyone's going to have a custom solution. This, once again, this depends on where your data is coming from, what kind of rules you're looking at, what you really need, who's going to be writing these rules. Is it engineers? Is it analysts? Every single business is going to need a custom solution. You need to know what your data is. You need to know your objects. You need to serialize your objects. You need to know what you want to find out so you can optimize your implementation on top of MapReduce for the rules that you are writing. Because as I showed before, there's two different ways to implement it. You can do it in the mapper, you can do it in the reducer. You might even need to do work in both. I don't know your data set. I don't know what you want to find out. You need to think that through and write your own MapReduce jobs based on that. Figuring out the execution of rules is a very important thing, as I showed. I could run everything in mappers. I could sort my data. For example, with the second example, I could pre-sort my data, run everything in mappers. I didn't do that. Maybe that'll be faster. Who knows? There's a lot to think through. There's a lot of different ways that this can work out, and you just have to experiment and see what works for you. Make sure your beans are serialized. This is a big issue I ran into the first time I tried running this, is this recursive serialization that needed to happen. You learn. And your mileage will vary. There's no solution that is one size fits all. You have different needs, you have different capacities, and you have different clusters, you have different data sizes. Figure out what needs to be run on Hadoop, what doesn't need to be run on Hadoop. Maybe you have rules that are run against a couple thousand data sets, and then you have others that are run against yearly billions of records at a time. Run half of them on Hadoop, run half of them not off of Hadoop. Once again, custom implementation for every single organization. So, yeah, that's my talk. All right, any questions?
We got an application in ilog JRules. It runs in WebLogic. What's the best way to migrate to Hadoop?
If you already have rules?
Yeah, we got thousands of rules written there. It runs in WebLogic.
Sure. So, because your rules are already written, and like I said in the beginning, a lot of this is plug and play. So, all you really need to do is set up this infrastructure to run your rules. So, I don't know your rules, but for example, if all your rules are simple, look at this record and exclude it, or look at this record and modify it, and it's only one record per, one record per rule, it only needs access to one record, then you can create one MapReduce job really that will simply take in records, and each mapper will run its own subset of records and analyze them. If you have more complicated rules, you might have to reevaluate this. This is really about knowing your rules and knowing how the MapReduce job should be structured. Yeah?
So if you have a large number of rules, the number have been given by rules engine vendors, more than 20 or more than 50, that big advantage of rules engine is the Reedy algorithm will compute the dependencies between all the rules for you to figure out which rules to fire. And that trying to manage that process yourself results in an explosion of code complexity. So if you're now saying rewrite all your rules in Java and run them on a Hadoop cluster, are you faced with throwing out the Reedy algorithm?
Not quite. That's a good point. So this is what I meant by read up on the implementation of your engine. I didn't mean that you have to rewrite your rules. I meant write your infrastructure to support your rules. So you have all these rules already, and your infrastructure will simply be like one big engine that distributes the work to the Hadoop cluster. So you can still feed in all the rules into this engine as long as it's doing the right sort of processing. So like I said, if you have aggregation rules, then you're going to need to, it's going to work a little differently because you won't be able to process them all in one JVM. But you can still feed in all your rules, and the Reedy algorithm will still work and figure out what rules need to be fired against the data set. It just depends on how you implement the engine, where you implement the engine, the mapper and the reducer, and what data is being fed into it. In this case, the mapper and the reducer are simply ways of feeding data into the engine. Are there any more questions? All right, great. Well, thanks for listening, and I'll be up here if you have any more questions.